Can you feel the love tonight? No, I can't feel a thing because it's so hot and sticky. I thought Laramie was not supposed to be humid, but let's talk about the picture that we use for confidence intervals. We've talked about the equation and how you get it, x bar plus or minus your z, sigma over square root of n. These guys have names. We have standard deviation, standard error, and margin of error, like this. But instead of talking about the equation, let's talk about the picture for it. So here's my great big picture, and it's centered over mu. The bad news is we don't know the value of mu. We know it exists, but we don't know what the number is. So what we're going to do is we're going to say mu should be close to x bar. X bar we do know. We just don't know whether x bar landed below mu or above mu, so it's not like we can use x bar to solve for mu. So from mu, we create these bounds, and that's what we call the margin of error. So margin of error is supposed to belong to mu. When we stick it on x bar, we're actually stealing it because mu is fixed with one set of bounds. Now, x bar is random. I realize you're only doing it once, but that once means x bar could land here, or here, or here, or here, or here. Now, does it ever land outside the bounds? Yes, but only if it was a 95% confidence interval, only 5% of the time. The rest of the time, it's always landing in here. And understanding that picture is really important to understanding the wording. And the next video is going to be about the wording, and it's one of the top 5 hardest things in this class. Probably one of the top 2 or 3 hardest. Let me draw this same picture a different way. Here I've got mu, and I'm going to give him this long, tall line, and he has this bound based on margin of error. So x bar is supposed to be landing inside this blue range 95% of the time. So let's say I do a study, and I get x bar right here. Yes, he is in the range. And so if I take this range and I give him to x bar, he'll be something like this. So because x bar was in the range of mu, mu is also in the range of x bar. Let's do it again. The next time my x bar is a little bit closer to mu. I realize you only get one x bar, but let's imagine that lots and lots of people are doing this study. Another person does the study. They get an x bar. It's a little further out, closer to the edge. Well, by luck, that can happen. Most of the x bars are close into mu. This guy got an x bar that was clear out there. For each of these x bars, let's put the bounds that we steal from mu and put them on the x bar. It would look like this. So for every one of these intervals, the bounds, because it was in the bounds for mu, mu is in the bounds based on x bar. Now I purposely did this 20 times. There's 20 x bars, 20 people doing this study, because if we're working with a 95% confidence interval, then x bar could land outside this blue bound, and it should 5% of the time. If I have 20 dots, we would expect one of them to have landed outside, and here he is. This average landed outside the bound, and because of that, his confidence interval does not contain mu. And I'm sorry, that's bad luck, but there's no way for you to do science and guarantee that you'll never get a bad luck answer, something wrong. But it only happens 1 out of every 20 times. Why is this picture important? Because I need you to understand, the method works 95% of the time, but after you've done it, either the confidence interval did capture mu or it did not. Now, before you do it, the chance that it will not capture mu has probability. After you do it, there's no probability. This is done. It did not capture mu. Also, I need you to notice, it's not that mu is changing. Mu is in some of these intervals and not in some of these intervals, but mu stayed the same. What changed was the random sample that you took, which changed x bar. And that will help us in the next video to define some of the correct language for confidence.